Hello and welcome to Auten Math. We have an exciting agenda lined up for today. We're going to talk about logs, graphing logs, and evaluating log functions. So let's jump right into it. Okay, some log basics. Log base b of y is equal to x is the same as b to the x is equal to y. All right, so we talk about exponential form and we talk about log form. And we've been dealing with exponential form equations for a long period of time. That b to the x is equal to y, that's an exponential form. Log form just changes the pattern around and places a word called log in front of the entire equation. So now I have log base b of y is equal to x. Now b of y is not the same as b to the y. Right? So log base b of y does not equal b to the y. It's something different, and we rewrite it in exponential form as b to the x is equal to y. So b now to the x is equal to y. All right, so as I've described it again, for b, log base b of y is equal to x is described as log base b of y, not to y, is equal to x. All right, logs are generally used to determine the value of a variable as an exponent. So if I were to give you a problem, solve for x, and I said 5 to the x is equal to 25, that's pretty easy. But when I say what's the value of x, when I say 5 to the x is 39. And this is where logs will help us out. So we'll get to this point where we can solve this problem. But for now, let's just say that our goal here is to be able to solve for this variable as an exponent. So as I mentioned again, log base b of y is equal to x is in log form, and b to the x is equal to y is in exponential form. They both mean the same thing. And I tell my students, you're learning a math language. We've already learned how to say or speak a language where we provide some value to be x and y in this form, and now we're just assigning the word log and changing the letters around. So I have my students as an assignment draw pictures, and maybe you can do this at home if you want. I write something in log form that's fun, so I say log, and I guess given the time of year, say log of a heart to, let's say, a house. I'm sorry, log to a heart of a house is equal to a person, right? Now that's in log first. So log base heart of a house is equal to a person. Now I can rewrite. I'm just going to rewrite this in exponential form. It would be heart. See if you can figure out what the next step would be. Now to a person is equal to the house. Okay, so the heart and the house are, the heart is like a subscript of log. The house and the person are on the same line here. The person is now changed in exponential form as the exponent, and the house becomes the value of taking the heart to the value of the person. It's equal to the house. All right, so just don't get mixed up or confused. Sometimes math tends to be a little austere, just in using numbers and letters. But if we use pictures, it makes it a little bit softer, and really it shows how easy it is to remember the simple pattern. Okay, special logs. A common log is a log with a base of 10. So I'd say log base 10 of y is equal to x. It can be simply written as log base 10 of y is equal to x, where I do not have to fill in the 10 as a subscript here. I just leave it blank. So if there is nothing written, as in this case, then we'll just leave it empty, this subscript empty, and we'll assume that it's 10. That's a common log. A natural log is a log with a base of e. So log with a base of e of y is equal to x can be written as ln, or natural log of y, is equal to x. So again, when you see ln is equal to log with a base of e. And remember, e is just, it's not a variable, it's just a number that's equal to about 2.72. Right, inverse logs. Inverse logs. I have log base b of y is equal to x is the inverse of b of y. So let's think about this. I say b to the x is equal to y. And remember, inverse, I'm just exchanging the x and y's value, x and y value. So b to the y is equal to x. So when you try to find out what the inverse log is, you're going to write the original function. You're going to rewrite the function in exponential form. You're going to then switch the x and y values, keeping the base the same, and then you're going to solve in terms of y. So let's go through an example. I have y is equal to the natural log of x plus 3. Okay, now I have log base e, right? So I convert this just to express it as a base of e to get the base in here. Log base e of x plus 3 is equal to y. Now I'm going to rewrite this in exponential form. It's e to the y is equal to x plus 3. Now I'm going to switch the x's and the y's. Now I have e to the x is equal to y plus 3. And now I solve for y. Y is equal to e to the x minus 3. It's that simple. All right, so inverse logs. Now if I have log base b of b to the x, then that's going to be equal to x. So let's see what that means. If I say log base 7 of 7 squared, right, then the answer is going to be 2. Because I have 7 squared is equal to 7 squared. If I have a log base 9 to the 9/5, that's going to be the same as 5. Right, so log base b, b to the x, is equal to 5. Now we run into problems sometimes where we have log base 9 of 81 to the 5th. And we can rewrite this as log base 9 squared, because that's 81, taken to the 5th. 9 squared taken to the 5th is 9 to the 10th using the power of the powers. So I can rewrite this as 9 log base 9 of 9 to the 10th now is equal to 10. Okay, another inverse log, let's say formula or pattern that you'll see. If I have b, so the log base b, b log base b, so as you remember it's unstated, 10 of 4 is equal to x, right? So I have 10 to log base 10 of 4 is equal to some value, right? So I say log base 10 of 4 is equal to, let's say it's y. That means 10 to the y is equal to 4, okay? So log with a base 10 of 4 is the same as y, right? So I have log base 10 of 4, it's equal to y. I can rewrite this as log, or 10 to the y is equal to 4. Okay, so log base 10 of y, log base 10 of 4 is equal to y. I state that equality, and I say that's equal to 4. Now I know that 10 to the y is equal to 4. Right, so now I have, again, 9 log base 9 of 7, and that's going to be equal to 7. Right? These take a little bit of practice to figure out. They're not that difficult, and I'm sure that after some practice and working with these in the practice section that you'll become very proficient at it. Okay, graphing log functions. I have g of x is equal to b to the x. Now what happens when b is greater than 1? What happens to the function? When b is greater than 1, this looks exactly like an exponential growth function. All right, my domain is all real numbers because I can substitute any value in for x and get a real number result for y. My range is going to be greater than 0 because regardless of what I put in or substitute in for x, I'm going to get a positive value for y. All right, so if I were to plot this, it would look something like this graph, which is like an exponential growth curve. All right, now this looks exactly like an exponential decay curve when b is between 0 and 1. Again, x is all real numbers, so I can substitute any value in for x, get a real number result for y. And regardless of what I put in for x in this case, regardless of what I put in for x in this case, I'm going to get a value that's going to be positive out for y. So let's just assign some type of equation to this function. So y is equal to, let's say, 3 to the x, right? As x gets larger and larger, the y value gets larger and larger. In this case, I say y is equal to 1/3 to the x. As x gets more and more positive, y becomes smaller and smaller, smaller and smaller fraction. As x becomes more and more negative, right, I have a negative exponent, I take the reciprocal of the value. So as x becomes more and more negative, then this curve, the y value becomes more and more positive. So again, I have an exponential decay curve, which looks something like this. All right, moving on to the next couple of examples. Graphing log functions, and we've already gone over this. All right, now we're going to talk about what a graph of an inverse of a log function looks like. So remember, the inverse of b to the x is going to be log base b of x. Right, so I said, we'll say b to the x is equal to y. Right, and now I'm going to say log base b of y is equal to x. The log base b of x is equal to y. So these are the same. I have one equation in exponential form. I have one equation in logarithmic form. So if I want to write the inverse of this function log base b of y is equal to x, then it would be log base b of x. So you can see that these two are inverse functions of each other. So when b is greater than 1, remember the inverse function is just a reflection over the x is equal to y axis. And I've graphed initially the function b to the x is equal to y. And it looks something like this. So I'm going to say this is b to the x is equal to y. And now I want to graph log base b of x, which is the same as b to the y. And you're going to end up with a curve, again, that is translated or reflected over the y is equal to x axis. And it's going to look something. Oh, wrong color. Let's use red for this. It's going to look something, the reflection will look something like this. Okay, so I have a reflection. This is b now to the y, or I can restate this as log base b of x. So the inverse of the function, this is what I want you to know, the inverse of the original function when b is greater than 1 is going to be a reflection over the y is equal to x axis, and it's going to look like this graph. Okay, when b is between 0 and 1, again we have a reflection of the exponential decay curve, and if we were to write the exponential decay curve, remember it looks something like this. Right, so the exponential decay function looks something as I've drawn here. And again, this is b to the x is equal to y, where b is between 0 and 1. Looks like an exponential decay function. Now I'm going to draw my y is equal to x line. And then the inverse of this function is just going to be a reflection of the graph of log base b of y is equal to x. And it's going to look something like this. All right, and so this again is b to the y, or I could say, write this in a little bit nicer pen, I could say log base b of x. So again, the inverse function. So we're graphing inverse log functions here. All right, let's move on. Last part. So again, all I want you to know for my class is just that the inverse is going to be a reflection over the y is equal to x axis. If you see a function like this, then you should know basically that you're going to reflect the parent function over the y is equal to x axis. All right, let's talk about translating functions. So this is very similar to the translated function for exponential growth and decay, where h represents the horizontal shift. So I have log base b of x minus h plus k. K represents the vertical shift. So I have y is equal to log base x of x minus 2 plus 4. I shift the graph 2 units horizontally and 4 units vertically. All right, so when you see a function like that, then you know that you're going to make that shift relative to the form. So let's take on one problem. I have log y is equal to log base 2 of x is equal to y. So let's rewrite this in exponential form. I say 2 to the y is equal to x. and I'm going to create my table here. All right, and I'm going to substitute in values for y first and then for x. I'll put x here and then y. So when y is -1, then x is equal to 1/2. It's a positive 1/2. When y is equal to -2, we really should go in ascending order, but let's just, x is equal to positive 1/4. When y is equal to 0, x is equal to 1. When y is equal to 1, x is equal to 2. When y is equal to 2, x is equal to 4. When y is equal to 3, I have x equal to 8. Okay, so let's plot these points. I have x at plus 1/2, y at -1, x at 1/4, y at -2. And you can see that the asymptote is going to be the y-axis. I have x at 1 and y at 0, x at 2, y at 1, x at 4. And again, I tell my students there's really no magic trick. You just have to take a look at what's happening in the function, create your table, and then over time you'll be able to identify the general look of what the graph will be. X is equal to x is equal to 4, y is equal to 2, x is equal to 8, and y is equal to 3. All right, so my general color of the graph looks something like this. Let's do this in black, and we'll see that the asymptote is going to be x is equal to 0. So regardless of the value for y, or x will never be equal to 0. Now I want to graph the function. Function shifting it now to the right 2 and up 4, and let's plot in some values and see what we get as a result. So I'm going to say this as, actually what I'm going to do is I'm going to rewrite this particular function in exponential form, and then we're going to go ahead and graph a couple points. So the first thing I want to do is I want to rewrite this in exponential form to create my table. All right, and this can be a little bit tricky, but again, this is a learned skill over time. I'm going to rewrite this in exponential form. First, I have to isolate this value x minus 2. So I'm going to subtract 4 from both sides. So I have y minus 4 is equal to log base 2 of x minus 2. And I can rewrite this in exponential form. It's going to be 2 to the y minus 4 is equal to x minus 2. And then I want to isolate x on the right hand side, so I'm going to add 2 to both sides. And I have 2 to the y minus 4 plus 2 is equal to x. All right, so I'm going to erase all this here, and let's create a table with some points. And again, this is just some work that you have to do. I have my x values and my y values. All right, so let's say when y now is equal to 3, I have 3 minus 1, so 2 to the -1 is going to be 1/2 plus 2, I get 2 and 1/2. 2 and 1/2. When y is equal to, let's say, 5, I have 5 minus 4, 5 minus 4 is 1, 2 to the 1 is 2, 2 plus 2 is 4. When y is 7, I have 7 minus 4 is 3, 2 to the 3rd is 8, plus 2 is 10. All right, so this is about as far out as I think we can go for now. And let's just put another value here, 6. When y is equal to 6, 6 minus 4 is 2, 2 squared is 4, 4 plus 2 is 6, so 6 and 6. So I have 4 points here, and we're going to plot those in red. So I have 2.5 and 3, 2.5 and 3 here. And then I have 4 and 5, 1, 2, 3, 4, and 5 here. And then I have 6 and 6, 1, 2, 3, 4, 5, 6, and 6 is going to be somewhere over here. Now I'm starting to get into my graph. And then I have 10 and 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 7 looks something like this. All right, so if I were to graph this, I see that this value should be a little bit to the right-hand side of Having a hard time drawing with this pen. Should be to a little bit of the right-hand side of 2 because the graph, this value will never be 0 or less than 0. So I will always have a value of x that's going to be greater than 2. So my asymptote is going to be x is greater than 2, or x is equal to 2 is my asymptote. And you can see my function here is just shifted to the right 2 and up 4. So again, shift to the right 2 and then up 4. And that's what the graph has told us is going to happen, right? That's what the translated function has told us. So I shift to the right 2 and up 4, and there's my graph. All right, a lot of content for today. Very good listening to the entire lesson. Why don't you come back and join us for a couple of practice problems and not in math in evaluating logs and graphing log functions.